All right, hello everybody. Today we're going to be doing loop analysis examples. And if you haven't seen the video on how to do a loop analysis, please check that out first. We're just going to go through all of these. I've got three practice problems planned out to highlight some of the important configurations that I think you're going to see during your time of studying loop analysis. So let's just get right through into it. So we're going to do step one. And for all of these, I'm going to choose a counterclockwise current because that is going to be in the direction of our currents of interest, which is IA and IB. So I'm going to go ahead and draw those loops. And the reason why I'm doing that is so that we have things that are already in the direction of IA and IB. So it's just simpler to get the answer once you've calculated it all out. Oh, and we're going to label them I1, loop 1, loop 2, I2, loop 3, and I3. So step 2, we're going to do KVL, or the loop analysis. And we're going to just go through each loop. Now I want you to pay special attention here. We have the 10 ohms going this way, and we have I1 going up, and we have I2 going down. So make sure to take into account those guys. So we have I1 minus I2 here. Plus 5I1, because we only have I1 going into the 5 ohm resistor, equals 0. I'm going to go ahead and simplify this. And we get 15I1 minus 10I2 equals 12. Now we're going to move on to loop 2. I'm going to go ahead and start right here, and I'm going to walk around. Once again, you got to take into account the 10 ohm resistor having current I2 going into it and current I1 going into it as well. So we're going to do 10 I2 this time minus I1 because our perspective has changed. Then we got the 15 ohm resistor with just I2 in it. And finally, we have the 30 ohm resistor with I2 in it and I3 in it. Okay, we're going to go ahead and simplify this down. And we get negative 10I1 plus 55I2 minus 30I3 equals 5. Last one. I'm going to go ahead and start right here. We're going to go up through the 15 volt battery through the negative side, walking to 20 and walking down to 30. And there we have it. We have our 3 equations and 3 unknowns. Let's go ahead and put this into a matrix form. All right, now let's go ahead and put this into the calculator. And we are going to get I1 equals 1.283, I2 is equal to 0.725, and I3 is equal to 0.735 amps, amps, and amps. Okay, these are not our answers. We've specifically been tasked to find IA, right? IA and IB. Now, IA is directly given to us. It's just I1 because we just have I1 going through the 5 ohm resistor. So, right here, we're going to say step 3 answers, right? So we can say IA is equal to I1 is equal to 1.283 amps, okay? Now for IB, we're going to have to be a little more careful about this. So like I said before, ideally you're going to want to you're gonna want to use KCL. It's just more reliable in my opinion. You could do it. I'm going to show you both ways. So let's go ahead and use KCL. So we're going to take this node right here because this node combines IB. You could take this one as well, although I wouldn't because that's just confusing. It's just easier to look at things at the top. I don't know why. But essentially what we're going to recognize here is that we have I2 coming out of the node here, right? And remember, we're using our convention. Oh, and then also, just a side note, notice how these values were all positive. That means that all of the directions that we chose were correct. That means all of the currents are going in a counterclockwise fashion. If we chose this one to be going clockwise, then this one would have been negative, right? I2 would have been negative. Anyway, that's a side point. So we can both say that by our coordinate system and the physical interpretation of the actual current, I2 is going to the left. But ideally, you're just going to want to say from your coordinate system that you picked, I2 is going to the left out of the node. Okay. And then I3 by our coordinate system that we picked, it just so happened to be physically true. I3 is going into the node. And then IB is our unknown, so we're just going to keep that as going out of the node as positive. So we're going to do a KCL right here. And we're going to say I2 is going out of the node, which is positive. I3 is going into the node, which is negative. And IB is going out of the node, which is positive. And manipulating this, we get IB is equal to I3 minus I2. And then IB is equal to I3, which is 0.735 minus 0.725. And after plugging that into the calculator, we get roughly IB is equal to 0.009 amps. Okay? And you can be more precise and say downwards, okay? Because it's a positive relative to our coordinate system, so then that means the direction that we had chosen, or technically the professor or whoever chose this, in this case I chose, IB going down, and we got a positive value. So this is the answer, IB, and this is the answer, IA. And of course you can plug in all of these, you can plug all of this into these equations and you should get the same answer. Now, the other way that I was talking about, remember, is you can use these right here. However, you need to recognize which one is actually going in the physically correct direction. We know this one is going in the physically correct direction because of our nodal analysis, or not nodal analysis, or KCL right here. Because we found that I3 is actually going into here, and we have to subtract, I'm sorry, I got that backwards. Or rather, I'm sorry, it would have been the absolute value would have been the same. It would just depend on whether or not it was positive or negative. And then from there, you're going to have to determine, either way, you're going to have to use KCL to actually determine the correct interpretation of where the physical current is going. So long story short, I would just use KCL. All right, guys, let's keep moving forward. Problem 2. And I just realized that I had lesson 14 on the other example. This is lesson 15, guys. Yeah, sorry about that. Anyway, alrighty. So this one has a few current sources in it. Now, the way that we solve for current sources is that we assign an arbitrary loop with our current source, okay? What do I mean by that? So right here, I can assign a loop of 3 amps going around the whole thing because it's touching this branch, or I can choose a loop like this because it's still touching the branch, or I can choose a loop like this because it's also touching the branch. I'm gonna go with this way because it's simpler. And same thing with this 4 amps right here. Okay. Now, here's the thing. We want to get I, right? We want to get this I right here. So our last loop can't be this loop, okay? Because then our I right here will just be 3 amps and 4 amps, and we're completely neglecting the fact that this portion of this circuit is connected to this portion. Okay? So that would be wrong. Okay? So what we are going to do instead is make something called a super loop. Okay? So as you saw before, a loop is literally just any closed path. So this is a loop, this is a loop, this is a loop, loop, etc., 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 right? So why don't we make a loop that encompasses this I, and it goes like this. Okay, oh, that just deleted everything. Okay, all right, and let's call it I1. Now, does this work? Well, yes, because it accounts for the fact that this power source, or whatever current is in this branch, does have a say in what goes on in this branch right here. Okay? And the cool thing about the super loop is that it greatly simplifies the number of equations that you would need. Okay? So let's go ahead and solve this just so that I can show you. Okay? So step 1, draw a loop. And then I'm going to put a note here, opportunity for super loop. And I say opportunity because there is another way of doing this, and it's called the brute force method. And we will not be doing the brute force method in this video. I plan on doing another video with a little more complicated circuits, or a little more complicated methods of solving these circuits with a combination of nodal and loop analysis. And brute force will be in that video, so you don't have to think about that right now. But so first we're going to draw the loop, and then step 2, we're going to do our KVL, or loop analysis. And and I will always call super loops as big L1. Okay? So we got big L1. And what do we got? We're going to start here. We're going to walk around this loop. We've got +1, plus, we've got 2 ohms. Now be careful here. We have I1 going in here, but what else do we also have going in here? We also have 4 amps going into this right here. Okay? So then that means we're going to have I1, and I1 is going in the same direction as 4. Plus, now we're going to go through this 1 ohm resistor. Now this 1 ohm resistor is really special because it has a whole lot going on. We've got the I1 going in, right, from this loop. We've got 4 going in the same direction. Excuse me. And we've got the 3 amps going down. Okay, so we've got I1, 4, and 3. Okay, that is very important. Okay, plus we've got the 3 ohms. Now we've got I in there, I1, sorry, and then we've got -3 amps because we're going this way. 3 and I1. And finally, last but not least, we've got 2i1, and then all that equals 0. So we're going to go ahead and simplify this. And we get I1 is equal to negative 1/8. Now, once again, this is not the answer. Okay, we only found I1. If we were looking for this current, we would be done. But we're not. Okay, we're looking for this current. So once again, we are going to apply KCL. So we've got the I going in. We've got the 4 amps going this way. Now here, we've got the I1 minus the I1 minus the 3. Okay? Because we've got the 3 going into the node and the I1 going out. So our KCL will look a little something like this. I minus 3 plus 4 minus I equals 0. And we get I equals I1, that's I1. I equals I1 minus 3 plus 4 plus 1. And we get I is 7/8. And notice 7/8 amps is going up and our value is positive. So then that means the designated direction is correct. So this is our answer. And here is our last problem, problem 3. Now this may look a little scary. It definitely was very scary when I was first starting out, and I'd get these ones wrong all the time. Anyway, but we're literally just going to apply the exact same principles. So step 1, draw loops. So first I'm going to draw one like this. Okay. And so this means that this current's going out this way, right? So that's going to be I1. And this right here, I'm going to draw the loop going this way so that we have I2 and then this one I3 both going in the same direction as I for easier calculations. And we are going to simply make our loop equations, which hopefully you guys should be able to do now. So we're going to do loop 1, which is minus 10 plus 6I1 plus, pay attention here, 2I1 going in through minus I2 because these two are opposing each other. And then in the same equation, we have 1 and an I1, and this time these two are aiding each other in going down. So it's I1 plus I3 equals 0. And we'll just solve. Or simplify, sorry. And we get 9I1 minus 2I2 plus I3 equals 10. Now we're going to do loop 2. That's just going to be negative 2 volts, 2 ohms, and 1 ohm. So negative 2 plus 2 ohms, 2 times I2 minus I1, because remember, they are opposing each other. We're this time going in from the I2 direction, plus I2. Because 1 times I2 is just I2, equals 0. Now we're going to simplify. And we get negative 2 I1 plus 3I2 equals 2. The last one, loop 3. We've got the same configuration, negative 2 in this way, 1 and then 4. So we've got negative 2 plus 2 times, I believe we said it was I3 plus I1, because these two are going in the same direction. I3 and I1 are going in the same direction, so we're going to put them as plus. Plus 4I3 equals 0. And we're going to simplify. And we get 2I1 plus 7. Sorry, I think I made a mistake. Yep, it's 2 ohms, not 1. I mean, it's it's 1 ohm, not 2. 1 right here. So then that means this would be I3 and I1. And we will get 5I3 equals 2. And this will be I1. So our last equation would be I1 plus 5I3 equals 2. Now, taking these equations, we're going to go ahead and turn them into a matrix. Also, I feel like I need to tell you guys this. You do not have to put in a matrix every single time, but it does help you keep track of everything, okay? And it prevents you from being lazy and making very careless mistakes. And if we put this all in the calculator, we get I1 is equal to 1.469, I2 is equal to 1.642, and I3 is equal to 0.107. And I bet you guys can guess, these are not the answers. We are looking for I, okay? So what are we going to do? Well, we're going to do KCL at this node right here. So step 3. I guess you can say KCL or answer, whatever you want. And now we're going to identify what is going into what. So right here, we have I1 going in. We have I2 going out. So our first branch, our first branch would be I2 minus I1 plus, and we've got I1 and I3 going out. So we've got I1 plus I3 going out, and we've got I going in equals 0. Notice that the I1s cancel out, and we get I equals I2 plus I3, and ultimately that simplifies down to 7/4 amps. And this makes a lot of sense, because right here we've got 7/4 amps, which is 1.75 amps, and we've got 1.642 going this way and 0.107 going in this way, and lo and behold, we get the 1.75 amps, and likewise from this direction as well. So our answer is 7/4. Now, I would highly encourage you guys to redo these. I did not check them this time. I am trusting that you guys know how to check them now. All you have to do is just replug them back in. And I would very much encourage you guys to find the nodes, the nodal voltages, of these. Actually, you really don't have to, because it's 2 volts. Okay, scratch that question. But essentially what I was going to say is that you can solve these problems in the same way as using the opposite method. So you can use nodal analysis on this, because remember, nodal analysis is just the currents, right? The sums of the currents. And so you could find this I right here. It may be a little more work, but you could definitely figure it out. So I'd highly encourage you guys to do that. I'm going to make a video trying to use nodal analysis and loop analysis. Ideally, you should get the same answer the same way. And if you ever have, like on your homework or something like that, and you want to be for sure that this is the right answer, then do both methods. Now that you know both methods, try both methods. All right, see you guys.